We have completed two subjects, that is analytical geometry and calculus. So today we will be starting a new subject, that is real analysis. We are starting with real analysis because there are certain topics that are common in between calculus and real analysis. So it's better to go in that way. So we are starting with real analysis, and the first subtopic in real analysis that we'll be dealing with is uniform continuity. So first let us just see definition of a uniform continuity, and then we'll move on to see other questions that were asked on this topic. So first let us see the definition of uniform continuity. So a function f from, let's say, domain D to real line is said to be uniformly continuous. Said to be uniformly continuous on domain D if for given epsilon greater than 0, there exists a delta greater than 0 such that my modulus of fx minus fy is less than epsilon whenever my x minus y is less than this delta that we got based on the epsilon given. So that means that whenever these 2 points x and y are close enough, then their image is also very close. So the sequential criteria of uniform continuity says that if there exist two sequences, let's say xn comma yn be two sequence, and these sequences are such that xn minus yn, basically limit of xn minus yn approaches 0, then the function f from let's say domain D to R is said to be uniformly continuous if their image, that is fxn minus fyn, if their limit also approaches 0, then we say that the given function is basically uniformly continuous. This is sequential definition, and usually it comes handy while disproving that a function is not uniformly continuous, because in that we can just choose in two sequences that are whose difference is converging to 0, and then we can show that their difference of their image is not converging to 0. So that basically gives a contradiction to the sequential definition, and from there on we can conclude that the function is not uniformly continuous. Now there is another result that we'll be using, which says that if a function f is continuous on a closed interval a comma b, that is a compact set, then function is also uniformly continuous there. Then function f is also uniformly continuous on closed interval a comma b. That means that on a compact set a continuous function is also uniformly continuous. And the another result is if a function is uniformly continuous then it's continuous as well. But its converse is not true. That is, we cannot say directly that a continuous function is always uniformly continuous. On a compact set this result holds, but it is not true for every domain. So we'll see that later on. We'll see certain examples of it later. Converse is not true, but converse hold for compact set using this. It is called Hayne-Cantor theorem. So let's move on to see the questions on this topic. So the question 1 says that prove that the function fx that is defined as, so our function fx is basically sine of x square is not uniformly continuous on this interval. So our claim is that this function fx is not uniformly continuous, on interval 0 to infinity. So in order to disprove this, we'll use basically sequential criteria, and for that we'll let in two sequences. So let us assume that xn, that is our first sequence, be square root of n pi by 2, and further assume that yn, which is our second sequence, let it be n plus 1 pi by 2. Now we are choosing our n such that these sequence, that is difference of these sequence, that is xn minus yn, is less than delta, and here delta is some positive number, delta is greater than 0, and such an n would be basically greater than pi by delta square. Now if we calculate f of xn minus f of yn, so it will be modulus of sine under root n pi by 2 square minus sine under root n plus 1 pi by 2 square modulus, and it simplifies to modulus of sine n pi by 2 minus sine n plus 1 pi by 2. Now if you see that these two sequences, like their difference will always be equals to, like the absolute value of difference will always be equals to 1, because for example if I choose, let's say, my n to be 1, so it will be sine pi by 2 minus sine pi, and this value is 1, this is 0. Likewise if I take my n to be 2, so it will be sine pi minus sine 3 pi by 2. Again this value is 0 and this value is minus 1, so again its modulus turns out to be 1. So in every case its absolute value will be 1, so the difference turns out to be 1. So if I choose my epsilon equals to 1 by 2, then ideally for it to be uniformly convergent this should be less than epsilon, but for epsilon equals to 1 by 2, this is greater than epsilon. So this contradicts my statement. So we got a contradiction. Because we have two sequences xn comma yn such that xn minus yn approaches 0 as n approaches infinity, but fxn minus fyn, this doesn't approach 0 as n approaches infinity. So we got a contradiction. Also, how do I know that this xn minus yn terms approaches 0? So for that, like, you can either observe it, it's very simple. So if I just see that, like, let me do it here, I should have explained it earlier. So if I calculate my xn minus yn, so it is basically modulus of square root n pi by 2 minus square root n plus 1 pi by 2. Now if I just rationalize it, so what will I get? I'll get n pi by 2 minus n plus 1 pi by 2 divided by n pi by 2 square root plus square root of n plus 1 pi by 2, and it simplifies to modulus of minus pi by 2 divided by square root of n pi by 2 plus square root of n plus 1 pi by 2. Now if I take my n approaches infinity, this whole term will approach 0, and we are assuming that it is less than delta. So if this whole term is approaching 0, and so it will be 0 less than delta. So we got a delta positive such that xn minus yn is less than delta, and for that delta my fxn minus fyn is not less than epsilon. So this contradicts the sequential criteria of uniform continuity. So we can say that this function fx, that is sin x square, is not uniformly continuous. Now let's move on to see the next question. So the next question says that show that the function fx, that is sin 1 by x, is continuous and bounded in 0 to 2 by pi, but it is not uniformly continuous in 0 to 2 by pi. So first let's prove its continuity, and then we'll move on to show that it's not uniformly continuous. So in order to prove its continuity, so the given function is fx equals to sine of 1 by x. Now if you observe that it is basically composition of two functions, that is, if I take my function, let's say gx as sin x and my function hx as 1 by x, and both these functions are defined on interval 0 to 2 pi, because that's what the domain, that is what the domain of function fx. Now if I take composition of function g and h, that is g of h of x, so what I'll get g of hx. My hx is 1 by x, so g of hx will be g of 1 by x, and that basically gives me sine of 1 by x. So my function fx is basically composition of function gx and function hx. Now we know that if two functions are continuous, then their composition function is also continuous. Now sin x being a trigonometric function on 0 to 2 pi y is a continuous function. Likewise, only point of discontinuity on hx is basically point 0, but we are considering open interval 0 to 2 pi, so this also have no point of discontinuity, so it is also continuous. And since composition of two continuous function is continuous, so that basically gives me my fx, that is g of hx is a continuous function on open interval 0 to 2 pi. Now let's see how we can show that it's not uniformly continuous. Now again we'll restore to sequential criteria in order to show that it's not uniformly continuous. So for that, let us assume two sequences. Let my sequence xn be 1 2y 2m pi, and let my sequence yn be 2 by 2m plus 1 pi. Now if I see my sequence like xn minus yn, that is 2 by 2m pi minus 2 divided by 2m plus 1 pi, so it will be equals to 2 by pi 1 by 2m minus 1 by 2m plus 1, so that is equals to modulus of 2 by pi into 2m plus 1 minus 2m divided by 2m into 2m plus 1, and this balances out this, so it will be equals to 2 by pi into 1 by 2m into 2m plus 1, which is less than equals to 2 by pi times 2m into 2m, which is equals to 1 by 2m square pi. Now if I choose it to be less than delta, so I'll get my m as basically my m square is greater than 1 by 2 pi delta. So I am choosing my m such that this condition is satisfied. So my m is greater than 1 by square root of 2 pi delta. Now let's see what is my f of xn minus f of yn. So that will be modulus of sine 2m pi by 2 minus sine 2m plus 1 pi by 2. Now if you observe that its difference will, absolute value of difference will always be 1 no matter which value of m you choose. And if I choose my epsilon equals to 1 by 2, then this is greater than epsilon. So this basically contradicts the sequential criteria of uniform continuity. So we can say that our function fx is not uniformly continuous on open interval 0 to 2 pi. Now let's move on to see the next question. So the next question says that we have a function f from real line to real line and it is a continuous function. So we have a function f from r to r and this function is continuous. So I'm just writing continuous with CTS. And further it says that limit of fx as x approaches infinity and limit of fx as x approaches minus infinity. These two limits exist and are finite. So it says that limit x approaches infinity fx exists and is finite. So let us assume that it is equals to L. And it also says that limit as x approaches minus infinity fx, this limit also exists and is finite. So let's assume that it is equals to m. So our claim is we are supposed to prove that whenever these conditions hold, the function fx is also uniformly continuous on R. That's what we are supposed to prove. Now, in order to prove its uniform continuity, first let's see what all information we can extract from the given information. So this limit is given to us. We have assumed that this limit is L. So using the definition of limit, we can say that for epsilon greater than 0, there exists a number n. Let's name it as n1, which is also greater than 0, such that mod of fx minus L is less than epsilon by 2 when x is greater than n1. Likewise, if we write it like we can write this term as for epsilon greater than 0, there exists a number, let's say n2, which is also greater than 0, such that mod of fx minus m is less than epsilon by 2 whenever x is less than minus of n2. Now we are taking here epsilon by 2 so that we can balance it out in the later stages. You can take epsilon as well, that is also fine. Now if we consider an interval, so if we take our interval, let's say minus n2 to n1. Now since my n2 is greater than 0, so minus of n2 will be less than 0. So we are considering this interval. Now we know that the function fx is continuous on the whole real line, so it will be continuous on this interval as well. So function fx is continuous on closed interval minus n2 n1. And if you observe that this is basically a closed and bounded interval, it's a closed and bounded interval. And we know that a continuous function on a closed and bounded interval is uniformly continuous. A continuous function on closed and bounded interval is uniformly continuous. So this basically proves that our function fx is uniformly continuous on closed interval minus n2 to n1. Now if we are supposed to prove it that it's uniformly continuous on whole real line. Now second case arises when Okay, so, or maybe let's just take this interval as this, minus n2 minus 1 comma n1 plus 1, because if this relation holds for all n1, all x greater than n1, then this will also hold for x equals to n1 plus 1, and likewise this for n minus n2 minus 1. So let's consider this as our interval. So this is also a closed and bounded interval, and so using that we got that our function is basically uniformly continuous on minus n2 minus 1 to n1 plus 1. Now in order to prove that it's uniformly continuous throughout, we need to get a delta that works for all the cases. So for example, in this case, since we got it uniformly continuous in this interval, so we got that for given epsilon greater than 0, there exists a delta such that mod of fx minus fy is less than epsilon whenever mod of x minus y is less than delta, and here x comma y lies in this interval, that is minus n2 minus 1 to n2 plus 1. Now if let's say my x and y doesn't belong to this interval, because we need to prove it for whole real line, so if x comma y doesn't belong to this interval, that is minus n2 minus 1 comma n2 plus 1, because so in this case there will be 3 more cases. So first case will be case 1, when my x comma y both are greater than n2. So this one, both are greater than n1. So in this case my fx minus fy will be equals to, I can write it as fx minus L plus L minus fy, and herein I can use a triangular inequality that says that fx minus L plus fy minus L, and this is less than epsilon by 2, this is also less than epsilon by 2, because here my x comma y are greater than n1. So using this definition, these two are less than epsilon by 2. So from here I got that there exists a delta such that fx minus fy is less than epsilon whenever my x minus y is less than, let's say, delta 1 in this case. Now we need to choose, and here let's say it is delta only. Now there exists another case, that is case 2. So case 2 says that when both of my x and y are less than minus of n2. So in this case, if my mod of x minus mod of y is less than, let's say, delta 2, then what will be my fx minus fy? So I can write it as fx minus m plus m minus fy. Now I can use in triangular inequality here, so that basically makes it as mod of fx minus m plus mod of fy minus m, and this term is basically less than epsilon by 2, and this is also less than epsilon by 2 because of existence of this limit. So from here we got that mod of fx minus fy is less than epsilon whenever mod of x minus y is less than delta 2. So this is case number 2. In this case also my function fx is uniformly continuous. Now there can be a case wherein, like case 3, let's name it as case 3. So first let's just combine these 3 deltas. So let's say our delta note be basically minimum of delta comma delta 1 comma delta 2, because if it holds for these delta, then it will also, or wait, let's take it will be maximum of these deltas, because if it holds for these delta, like delta 2 and here delta 1 and there delta, then it will also hold for delta naught. So this is our delta naught. Now case third is when one of x comma y belongs to this interval and other doesn't belongs to this interval. So case 3 for, and without loss of generality we can assume that, let's assume that x belongs to this interval, and that is minus n2 minus 1 comma n1 plus 1, and let's assume that y doesn't belongs to this interval, that is minus n2 minus 1 up till n1 plus 1. Now in this case we can choose our delta to be, or maybe name it as delta dash, as minimum of delta naught comma 1. And why we are choosing so? Because like while proving a uniform continuity, we assure that these two x and y are close enough. Only then we can check that the function value at those points are also close enough. For example, if I choose, like if my delta, if in this case my delta is greater than 1, then x and y will have a distance greater than 1 units. So that doesn't make sense. So in order to avoid such case, we are choosing that our delta dash is a minimum of delta naught comma 1, and in delta naught is basically this, like maximum of all these three. And if you see that we have strategically chosen our interval as like interval with a buffer of 1 unit, like here and here as well we have already chosen a buffer of 1 unit. So if we observe it on real line, and let's say I'm just showing you for this interval, that is 0 comma n1 plus 1. If this is my n1 and this is my n1 plus 1, so like this delta dash will ensure that either both the points are here, like outside the interval, like the definition proves that it is continuous here, and like this delta 1 shows that it is continuous for all xy greater than n1, that is in this portion. And we have already shown that it is continuous in this. If this is my 0, we have already shown that it is uniformly continuous in this interval, that is on the left hand side of this. So we have chosen our delta dash such that like the distance doesn't go beyond this, like beyond this buffer. So this case basically ensures that either both the points lies inside this interval that we have chosen, or both the points lies outside that interval. So basically we can choose our delta dash as this, and this delta dash works for all the cases because this delta naught is covering all the above three cases, and this one thing is covering the buffer that we have chosen. So we got that for given epsilon greater than 0, there exists a delta dash that is defined as this, such that mod of fx minus fy is less than epsilon whenever mod of x minus y is less than delta dash. So this basically proves a uniform continuity for all the, like whenever the function is continuous throughout the real line and both the limits at endpoints exists and are finite. So let's move on to see the next question. So the next question says that they have given us a set X and it is closed on one end and it is open on other. So my X set is basically A comma B. It's closed on the left hand side, it's closed on right hand side and open from the left hand side. So they ask us to construct a continuous function f x to r, which is set of real numbers, which is unbounded and is not uniformly continuous on x. So the easiest function that can come to someone's mind is basically fx equals to 1 by x. But then we are supposed to construct it on this interval, closed interval a to, like this interval x, that is from open a to closed b. So let's reduce it. So it will be, let's assume that our function is x minus a. Now the function should be, if you observe that the only point of discontinuity this function has, x equals to a, but the set x has no point as a, so the function fx is continuous on interval a comma b, that is equals to x. And another condition for the function f is that it should be unbounded. Now if you take its limit as x approaches a, so as x approaches a, fx will be basically infinity. So this proves the claim that it's unbounded. Also, it further asks us to show that the function is not uniformly continuous on x. Now we'll show that fx, that is 1 by small x minus a, is not uniformly continuous on x, that is open a to closed b. Now in order to prove this, we will basically restore to sequential criteria. So let's assume that our sequence xn is equals to a plus 1 by n, and our sequence yn is equals to a plus 1 by n plus 1. Now if you see that xn minus yn, what is it? So it will be a plus, like mod xn minus yn, it will be a plus 1 by n minus a minus 1 by n plus 1. And it simplifies to n plus 1 minus n divided by n into n plus 1, and this is less than equals to 1 by n square. And for if this is less than delta, then by n should be greater than 1 by delta. So I got a positive delta such that these conditions hold. Now if I check my f of xn minus f of yn, so it will be equals to 1 by a plus 1 by n minus a minus 1 by a plus 1 by n plus 1 minus a, and that will be equals to n minus n plus 1, which simplifies to 1, and that is great. If I choose my epsilon equals to 1 by 2, this is greater than epsilon equals to 1 by 2. So we got that as xn minus yn approaches 0, our fxn minus fyn doesn't approach 0. So this basically contradicts sequential criteria of uniform continuity. So we get that our function fx is not uniformly continuous on interval a to b. Now in the question there is another subpart which says that would your function be uniformly continuous on this interval, that is a plus epsilon comma b. So we are supposed to check is fx, that we assumed as x minus a, uniformly continuous on interval, close interval a plus epsilon comma b. Now if you observe that this interval, let's name it as capital Y, the function fx is continuous on closed interval a plus epsilon comma b, because only point of discontinuity this function has is basically x equals to a, and that point is not included in the set y. So we can say that the function is continuous on the interval y, and if you observe that this interval y is basically closed and bounded interval, and we have a theorem which is basically Hien-Cantor theorem, which states that if a function is continuous on closed and bounded interval, then it's uniformly continuous on that interval. On that interval. So we have proved that our function fx is continuous and the set on which we are considering is basically closed and bounded set. So from here we can say that our function fx is uniformly continuous on interval a plus epsilon comma b. So this is what we are supposed to do in this question. So let's move on to discuss the next question. So the next question says that show that the function fx, that is sin 1 by x, is not uniformly continuous, and it is a repeated question. We have proved that it's not uniformly continuous, like we have proved this result question for 0 comma 2 pi 0 comma 2 pi, and you can, in a similar way, you can prove it for 0 comma pi. So you can do it yourself. Repeated question. So next question, let's see next question. So the next question says that show that the function fx, which is equals to x square, is uniformly continuous in this interval but not on R. Okay, so for this, let's assume that let epsilon greater than 0 be given. Then for some x1 comma x2 in this interval 0 comma 1, and we are choosing this x1 comma x2 such that x1 minus x2 is less than delta. Then what will be my f of x1 minus f of x2? So it will be equals to mod of x1 square minus x2 square, which I can write it as mod of x1 minus x2 times x1 plus x2. Now if you see that we have taken our x1 and x2 from this interval, open interval 0 to 1. So from here I can say that my mod of x1 comma my mod of x2 both will be less than 1. So if I use triangle inequality here, so it will give me x mod of x1 minus x2 2 mod of x1 plus mod of x2. This I got basically using the triangle inequality. And since this is less than 1 and this is less than 1, so this whole term will be less than equals to 2 times mod of x1 minus x2. And for it to be uniformly continuous, this should be less than epsilon. So from here I got my mod of x1 minus x2 less than epsilon by 2. So I can choose my delta as this. So if, like, for delta equals to epsilon by 2 for given epsilon greater than 0, we got a delta, that is epsilon. There exists a delta, that is epsilon by 2, which is greater than 0, such that mod of fx1 minus fx2 is less than epsilon whenever mod of x1 minus x2 is less than delta. And if you observe that the points, that is the point x1 and x2 in open interval 0 comma 1, we choose them as arbitrary points of those intervals. So from there we can say that this thing holds for all xy in that interval. So this basically gives us that our function fx is uniformly continuous on open interval 0 to 1. Now let's move on. I guess that's all we are okay. We are also supposed to show that it's not uniformly continuous throughout the real line. So for that, if I, like, we'll basically restore to sequential criteria. So now our claim is fx is not uniformly continuous on whole real line R. So for that, if I choose my sequences, let's say if I choose my sequence xn as n plus delta by 2, and I choose my sequence yn as, let's say, n only. So my xn minus yn will be basically equals to delta by 2, which is less than delta. Now if I take my mod of fxn minus fyn, and here also observe that we are choosing our n such that it is greater than 1 by delta, because then only we'll be able to show. So this is equals to f of xn will be n plus delta by 2 square minus f of yn will be n square. So this basically gives us n square plus delta square by 4 plus n delta minus n square. This n square balances this. So we got delta square by 4 plus n delta. Now from we choose our n such that it is greater than 1 by delta. So from here I'll get my n delta as greater than 1. And since my n delta is greater than 1 and this quantity basically delta square plus 4 is also something positive, so I can say that this quantity is greater than 1 and I can choose my epsilon as 1 by 2. So this quantity is greater than 1 and 1 is greater than epsilon, which I choose as epsilon equals to 1 by 2. So this basically proves that our that is fxn minus fyn doesn't approach 0 as n approaches infinity. So we got a contradiction via sequential criteria of uniform continuity. So this basically proved that our function fx is not uniformly continuous on this, not on whole real line, though it's continuous on open interval 0 to 1, but it's not uniformly continuous throughout the real line. So let's move on to see the next question. So the question is S is basically 0 to 1 and a function is defined as fx equals to 1 by x, where x lies in between, okay, x is from S, and we're supposed to check if f is uniformly continuous on S. So we have done a similar question above, so we can just choose to sequence xn as 1 by n and sequence yn as 1 by n plus 1. Now you'll observe that xn minus yn approaches 0 as n approaches infinity, but my modulus of fxn minus fyn, that will be modulus of n minus n plus 1. It will approach to 1 as n approaches infinity. So we got a contradiction to uniform continuity. This thing will approach to 1, not 0. So we got a contradiction. So we can say that this function fx is not uniformly continuous on interval 0, 1. Also, like in exam, you're supposed to write it properly, that we can take two sequence and all of that stuff. We have discussed similar questions previously as well, so that's why I just told you like this. So let's move on to see the next question. This is again repeated question. If you see that, like, there are only 2-3 questions and they are repeating them only again and again. Repeated question. Now let's move on to see another question. So this question says that, like, this is not a question that is asked in exam, but it is a theorem and it can be asked like maybe near future, so we can just discuss this. Like, this is basically a theorem. So it says that if function f is uniformly continuous on closed interval a comma b, then it has to be continuous on that interval, but the converse is not true. So first let's just see some example of converse, and then okay, first let's just prove it and then we can just discuss the converse part. So a function f is uniformly continuous. So f is uniformly continuous on close interval a to b. Now, by definition of uniform continuity, we'll get for given epsilon greater than 0, there exists delta greater than 0 such that mod of fx1 minus fx2 is less than epsilon whenever mod of x1 minus x2 is less than delta, and these x1 comma x2 belongs to this interval a comma b. Now let's assume that our x1 is equals to x. So the definition will reduce to mod of fx minus f of x2 is less than epsilon whenever mod of x1 minus mod of x minus x2 x2 is less than delta. And here if you see that we have taken like x1 and x2 arbitrarily from given interval. So this is basically definition of continuity only. So since our x2 and x are arbitrarily chosen, from interval a to b, so we can say that fx is continuous. This basically gives that fx is continuous at x2, and since we have chosen x and x2 arbitrarily, so this shows that fx is continuous at all points in interval a comma b. So from here we can see that fx is continuous throughout a comma b. Now let's move on to see the next question. Okay, we have another part as well. I guess it should have been an open interval, because a continuous function on closed and bounded interval is always uniformly continuous. So converse also hold for this case. So it should have been an open interval, like open interval a comma b. So an example for it will be, we can take this fx equals to sine 1 by x. We have seen that it's not uniformly continuous on 0 comma pi, although it's continuous therein. So we can take this example, and we have proved it in this video itself, so you can look at that. So let's move on to discuss the next question. Now let's discuss this theorem that we have used many times in this video, so which says that if a function f is continuous on closed interval a comma b, then it has to be uniformly continuous on that interval. So what is given to us, that we have a function fx and it's continuous. Fx is continuous on closed interval a comma b. Now we are supposed to prove that it's not uniform continuous. So what we'll do is we'll just prove it via contradiction. We'll just assume that let if possible that fx is not uniformly continuous. Fx is not uniformly continuous on closed interval a comma b. So if it is not uniformly continuous, then we should have two sequences. Then by sequential criteria we should have xn comma yn, that is two sequences in interval a comma b. Let's name this interval as I, such that these two sequences are such that a mod of fxn minus fyn is not less than epsilon when mod of xn minus yn is less than some positive number delta. Right, this is what we see in sequential criteria, like when it's not uniformly continuous. Now if you observe that we have taken these two sequences, xn comma yn belongs to I, and set I is basically closed and bounded. So if the set itself is closed and bounded, then these two sequences are basically bounded sequence. So from there we got that xn comma yn are bounded sequences. So if we use here Bolzano-Weierstrass theorem, so by Bolzano-Weierstrass theorem, every bounded sequence must have a convergent sequence. So it states that every bounded sequence must have a convergent subsequence. So if that's true, then both xn and yn must have convergent sequence. So xn comma yn have convergent subsequences. So let's say that this subsequence of xn is xnk, and that of yn is, let's assume that as ynm for time being. So let's assume that this xnk converges to xi and this ynm converges to eta. Now since our interval I is basically closed as well, because it's a compact set, since I is a closed interval, that means that I is a closed set as well. So we know that the closed set contains all its limit points, and these are basically where the subsequences xnk and ynm are converging. These are basically limit points of sequence xn and yn. So from there we got that closed set contains all its limits or all its limit point. So from here we got that xi and eta are basically inside this set I only, which is equals to a comma b. Now, so what we basically got is this, that we have two convergent subsequences. One of them is converging to xi and other is converging to eta. Now the sequential criteria of uniform continuity, we are choosing our xn and yn as this. So since the original sequence xn and yn are satisfying this relation, so their subsequence must also follow this relation. So from here we got that mod of xnk minus ynm is also less than delta, which we choose to be 1 by n. And if that's the case, if we take its limit, so it is limit xnk is equals to limit ynm, and since it is approaching to xi, so we got xi, and this is approaching to eta, so we got xi is equals to eta. Now we know that there is a similar sequential definition for continuity as well, which states that if a sequence xn approaches a as n approaches infinity, then for a continuous function fxn must approach f of a, right? This we got basically using continuity definition of continuity. So if we have seen that our xn approaches xi and yn approaches eta, and those xi and eta are same. Now since f is continuous, then limit n approaches infinity, f of xnk must be equals to f of xi, right? And likewise our limit n approaches infinity, f of ynm must be equals to f of eta. But since so from here we got that limit n approaches infinity, f of xnk minus f of y in m is approaching to 0. So we got a contradiction because we have seen we have assumed that this function is not uniformly continuous, so it is not less than epsilon whenever this thing holds, but we got two subsequences for which this thing holds and this is also approaching to 0, so we got a contradiction to our assumption. So since we got two subsequences, that is x n k and y n m, both of which converges to xi because xi is equals to eta, both of which converges to xi, but f of x n k and f of y n k doesn't converge to same limit, doesn't converge to same limit. So we got a contradiction to continuity. We got a contradiction to continuity. That means that if we assume that a continuous function on closed and bounded interval is not uniformly continuous, then we got a contradiction that the function is not continuous as well, but it is given to us that the function is continuous, so our assumption is basically incorrect. Our assumption is incorrect. So if our assumption is incorrect, that proves that our function fx is uniformly continuous. So from here we have proved that if we have a function on closed and bounded interval, that is this, then it is also uniformly continuous on a closed and bounded interval. So that basically completes our discussion on uniform continuity. There are only these questions asked in this topic. So we'll move on to next topic in the next video, and that will be most probably sequences and series. So thank you for watching, and please do like, share and subscribe the channel.